Today, we're going to talk about a number that for centuries, people were convinced couldn't possibly exist. A number that seems to break one of the most basic rules of math that we all learn. We're talking about a number that isn't, well, real.
You know, the number line, right? We all learned it. 0 in the middle, positive numbers stretch out to the right, negative to the left. Simple. But what if that's not the whole story? What if there's an entire universe of numbers that don't live on that line at all?
So, our story really kicks off with a classic mathematical headache, a problem that for the longest time just seemed to have no answer. And this is it. It looks so simple, so innocent. But this little equation was a real troublemaker. See, if you just move the 1 over to the other side, you get x squared equals -1. And right there, that's where the math world hit a brick wall.
Just think about it for a second. Take any positive number, like 2, and square it. You get 4, positive. Take a negative number, like -2, and square it. You still get 4, also positive. And 0 squared is just 0. There was literally no number on that entire infinite number line that you could multiply by itself and get a negative number. It felt like a dead end, a cosmic no. That is, until someone had a brilliant and kind of crazy idea.
So what do you do when the rules say something is impossible? Well, sometimes you just have to invent a new rule. You have to imagine a new kind of number.
And here it is. Meet I, the imaginary unit. The solution was this incredible leap of imagination. Mathematicians basically said, okay, if no number that we know of works, let's just create one that does. They just defined I to be the number whose square is -1. They called it imaginary almost as a joke, but what they'd really done was open a door to a whole new dimension of mathematics. And as soon as I existed, this whole new family of numbers came along with it, the complex number. Every complex number has 2 parts. You've got A, which is the real part. That's a number from our good old number line. And then you have the B part, which is attached to our new friend I. That's the imaginary part.
Now, I know what you might be thinking. A whole new kind of number? This is going to get complicated, right? New rules, new math. But what's so cool is that working with these numbers feels surprisingly normal.
Adding them up is a breeze. You just add the real parts together, and then you add the imaginary parts together. Done. And multiplication? It works just like the algebra you already know, with one simple extra step. Whenever you end up with an I squared, you just swap it out for a -1. That's it. That one little trick is the key to this whole new world. So far, this has all been symbols on a page, but the real aha moment, the thing that makes it all click, comes when we try to draw a picture of these numbers. This is where you really see what's going on. And that's the big question. If these numbers aren't on the one-dimensional number line, then where in the world are they? Well, they need more space. They need a second dimension. And here it is. This is the Argand diagram, or the complex plane. This picture changes everything. The horizontal line, the x-axis, that's our familiar real number line. But now we have a vertical line, a y-axis, for the imaginary part. All of a sudden, a number like x plus iy isn't just an abstract idea. It's a point. It's a specific location on a map, with the coordinates x, y. Seeing them this way makes operations like addition so intuitive. You can think of each complex number as an arrow, a vector, pointing from the center of the map to that point. If you want to add 2 of them together, you just place their arrows head to tail. The spot where you end up is the answer. It's elegant, it's visual, and it just makes sense.
All right, so if every one of these numbers is a point on this map, how else can we describe its location? Instead of just saying go over this far and up this far, we can think about it like a pilot would, distance and direction.
The distance from the center, the origin, out to our point is called the modulus, and you can figure it out in a snap with the Pythagorean theorem. The angle that line makes, measured from the positive real axis, is called the argument. So now we have 2 ways to pinpoint any complex number: over and up with x and y, or distance and angle with modulus and argument. Now, I gotta give you a heads up here because this is a classic trap that gets everybody. You might think, oh, I'll just find the angle by taking the inverse tangent of y over x on my calculator, and sometimes you'd get lucky, but a lot of the time you'd be wrong. Here's why. Your calculator isn't smart enough to know which quadrant your point is in. So the absolute #1 rule is you have to check the quadrant first. You find a little reference angle, phi,
using the positive values. And then, as you can see here, you just follow a simple rule depending on if you're in quadrant 1, 2, 3, or 4 to find the real angle theta. So remember, always check the quadrant. And just to make sure everyone's on the same page, mathematicians came up with something called the principal argument. It's just an agreement that will always use the unique angle that's between negative 180 and positive 180 degrees. It's a standard that makes sure everyone gets the same single answer. So at this point, you might still be wondering, okay, this is a pretty neat mathematical game, but what's it for? Well, it turns out this so-called imaginary number is one of the most practical and powerful tools we've ever invented. Take a look at this. This is Euler's identity. It's often called the most beautiful equation in all of mathematics, and you can see why. In one short, stunning line, it connects 5 of the most important numbers in the universe. You've got e, pi, our new friend I, and the fundamental 1 and 0. This isn't just a formula. It's like a poem about how everything in math is secretly connected, and complex numbers are the key that lets us see it. And this isn't just abstract beauty. This stuff runs our world. The design of the electrical grid that powers your house, the signals that make your phone and Wi-Fi work, the physics of quantum mechanics that describes reality itself, none of it would be possible without complex numbers. They're essential. This imaginary number is actually the bedrock of modern technology. So we started with a simple equation that had no answer, and we ended up with the foundations of the modern world, all because some mathematicians were brave enough to imagine a new dimension for what a number could be. And it kind of makes you wonder, doesn't it? What other impossible problems are out there just waiting for us to imagine a new dimension?